Chapter 11, Problem 19. A ball having mass m is fastened at the end of a flagpole that is connected to the side of a tall building at point P, shown in figure 11:19. The length of the flagpole is L, and it makes an angle theta with the horizontal. If the ball becomes loose and starts to fall, determine the angular momentum, as a function of time, of the ball about point P. Neglect air resistance. So for the givens, we have the ball having mass m, the length of the flagpole having length L, and the angle it makes as theta. And what we need to find is the angular momentum of the ball about point P. So, using our equation, r equals r initial plus the velocity vector times time plus 1/2 the acceleration vector times time squared. We can write that as the r vector equaling to, putting this in non-vector form, we get L cosine theta times I plus L sine theta times j for the vectors, plus 0 minus 1/2 gt squared as the j vector. So the velocity of the ball is defined as the velocity vector equals the initial velocity vector plus the acceleration vector times time, which equals 0 minus g, gravity, times time as the j vector. So angular momentum is defined as the r vector times mass times velocity vector. So we can simplify that to mass times, and substituting in values for r and for the r vector and v vector, we get L cosine theta I plus L sine theta j plus 0 minus 1/2 gt squared j times the velocity vector, which is negative gt j. And simplifying all this, we get the L, or the angular momentum vector, is equal to negative m L gt cosine theta k.